All right, guys, welcome to our third unit. We are going to talk in this unit about two-dimensional forces and two-dimensional motion. So to get things kicked off, we're going to introduce today this idea of what's called a vector. And today we're going to do some math about the different operations of vectors and vector quantities. Okay, so first of all, this word vector. What a vector is any sort of physics quantity that requires us to measure not only an amount, but to also indicate a direction. So key thing here is we are focusing on an amount and a direction. Now with an amount, you might also hear the word magnitude being used. But the key thing here, what makes something a vector, is that we have to indicate direction. So up to this point, we've learned about different types of vectors. We learned about, for example, displacement. That is a certain type of vector because we can move a certain amount of distance, but also we have to indicate the direction in which we move. We can talk about velocity, and then we can talk about the amount, which is the speed, how fast we're going, but we can also indicate a direction. We've looked at acceleration, which is the same thing, speeding up or slowing down, but again, that is dictated based on the direction. And then lastly, the whole unit we just finished was all on forces. So forces also, as we saw, you can think about things being balanced or unbalanced in our net force, were also things that needed a direction as well. So these are what are called vector quantities. Vector quantities differ from what's called a scalar quantity. Scalar quantities are the easy one. Scalar quantities only require an amount, okay? So it's whether you have that or whether you don't have that. So things that might require an amount, we have things like mass. We can look at like volume and time, okay? For example, time, it makes sense that maybe an hour goes by, but we don't usually indicate time with direction. Now, I know we talk about past, present, and future, but with time, it's usually a certain amount. Same thing with mass. Okay, we talked math last unit about the number of kilograms. Okay, kilograms was just how much stuff or how much inertia that object had. We did talk about that there was that relationship that if we did multiply kilograms times 10, we get the force of gravity. But again, that force of gravity was a force that acted downward on objects. But the mass itself was just a measurement of how much stuff that object was made of. So all scalar quantities are represented as strictly an amount. We do not have to indicate direction with those. So our goal in this chapter is we're going to look at we're going to kind of revisit some things we learned about already in terms of the variables of motion, variables of forces. But what we're going to do is we're going to get into things that are not just acting in one direction, but we're going to look at things acting in two directions. So direction is going to play a major role in this next chapter. So to do that, we're going to look at the ideas of vector quantities and how direction makes a big difference and how it plays a major role in some of these quantities. So to start off with, again, vectors are quantities that need a direction. So the very basic thing, this is actually stuff we've looked at last chapter in terms of forces. We looked at this in terms of distance and displacement. But the key thing is just being able to understand how direction is important. So let's say that I give you two vectors and our goal is to add them. Okay, so let's say that I want to add these first two vectors. Depending on what they are, you can think of them as, variables of motion, or you can think of them as forces. But when I see two vectors acting in the same direction, that they're going to combine to form a larger vector, and I would just figure out its magnitude by just adding those two numbers together. So if I add 5 and 5, obviously I get 10. That would differ then if we look at direction. If let's say I have 5 and 5 again, but now those two are going in opposite directions, those would actually combine to form nothing. I'll just put that as a point. So that would result in a total of 0, of whatever again that is, whether it's motion, whether it's forces. Okay, so again, in the same direction, we're going to add those vectors together. Opposite directions, they end up subtracting together. Okay, then the magnitude also plays a difference. So again, this looks at mainly direction, but magnitude does play a difference. That if something has more of an amount to it, that is going to supersede something. So here I have, again, 5, but I'm going to add to it 10. So what that's going to create is an overall vector, by combining those two, an overall vector of 15. So I would add them again being in the same direction. Versus in the opposite direction here, 5 and negative 10, what's going to happen here is that 10 acting against is going to overrule that 5, and there's going to be a resulting of negative 5. Again, it could be newtons, it could be meters. that's left over. So again, what happens here is I can still add these vectors, but when I have a vector going in the opposite direction, we can treat that as a negative, ends up being subtracting. All right, so why don't you pause the video real quick and try E and F on your own. So if I were to give you those two vectors, what would they add up to? So go ahead, pause the video, try it on your own. All right, take a look. So again, with E, they're working against each other, so I'm going to have to subtract those or treat that as a negative. So that means if there's 5 to the right, negative 15 to the left, that there's more to the left, so that would result in negative 10 to the left. This one for F, we have 10 up, 5 down. So again, those up and down would be resulting of 5 in the total in the positive. Okay, so this is again stuff that we looked at whether it was motion or forces. But the key thing here is that each of these examples represents one dimension. Now, yes, I understand that we have a forward and backwards or an up and down, left and right, whatever, but that is strictly acting in one dimension. Left and right would be treated as one. What's going to happen in this chapter is we're going to look at things in 2 dimensions. Okay, so 2 dimensions is where it's going to get sassy, and what that means is we're going to have a vector, say, working up, but we're also going to have something working right. So we have 2 distinct different directions going on in one sort of thing. So that's our goal in this chapter, is we're going to look at what are called 2-dimensional vectors. So 2-dimensional vectors are going to be any sort of vectors that act in 2 directions at once. Okay, so take, for example, here, say this is Chicago and we're traveling, let's say, up to Minnesota. I would go, in this case, follow this arrow would be maybe the direction of my motion, but this would be considered a two-dimensional vector because it is acting in 2 directions. The 2 directions it's acting, okay, would be it's acting to the left and it's acting up at the same time. Now, these 2 separate directions, these are what are called the components of a vector. So the components of a vector are the part of that vector in each direction. So while this vector goes here left and up, okay, I can draw that on here as it goes to the left and up, those 2 separate vectors that I'm drawing, those 2 separate directions are what are called the components. And that any 2 components make up what's called the resultant, and resultant is the overall vector form. So when I draw this picture down here, the 2 green arrows that I'm drawing, those are called the components. So the components would be the amount of whatever motion or force, whatever that might be in each individual direction. And the red arrow here would be the resultant. The resultant is obviously the result of those 2 motions combined. Okay, so what we get here is a 2-dimensional vector that has a part of its motion or its force, whatever we're going to look at, in each individual direction. Okay, now this goes back to the first example then, where we add and subtract vectors. Now we're just going to look at this without numbers. We're just going to look at this qualitatively with the arrows. So how do I add things that are acting in 2 dimensions? So let's take, for example, I have vector A, and I'm going to add to it vector B. But now notice they're not acting in the same direction. They're not acting against each other in opposite directions. But B is acting strictly to the right, but A is acting to the right and up at the same time. So A has what are called components. I'll draw these in green. So A is acting to the right and it is acting up at the same time. Okay. So to add these vectors, here's what I'm going to do. I'm just going to show you this by using what's called the head to tail method. So I'm going to draw one vector off of the other. So I'm going to start with vector B. So I'm just going to sketch this as best as I can. So let's say here there's B going straight to the right. And then I have A that is going up and to the right. And again, if my picture's not perfect, I apologize. Okay, so what ends up happening if I were to add these 2 vectors? A has a component that is going to the right, okay? It also has a component going up, and I'll draw that up arrow off to the right. And again, if my picture doesn't match, I apologize. But what ends up happening is if we add these 2 forces or 2 arrows, sorry, not forces, but arrows, if I add these 2 things together, here's what happens is it creates a resulting vector from where I started at B to where these 2 arrows would end. So I'm going to get a resultant vector. I'll draw it in black. That would look something like this. Now what ends up happening is when I add these 2 vectors, the vectors that are in the same direction, so here would be B, and then I will call this A with a little x, a subscript of x, to show that's the x component of A. What ends up happening here is that these 2 components, or these two vectors, would add together, so b and ax. And then we would also have the y component of a. All right, and what those will create then is my resulting vector. I'll just label this r. Okay, and notice what I end up creating when I look at the components of a is I create a large right triangle out of that. Okay, so this is just one way to visualize kind of what we're going to be doing here. But what ends up happening is when I add things that have two directions at once, is I have to talk or think about the components of that vector. I can do the same thing with a and b in example b. So if I have a going downward and b going to the left, what I'm going to do to add these is I'll just start with b again. And what I'm going to do to add these, I'm sorry if my arrows are not the same length, but that's really not the point here, is I'm going to draw a off the arrow of b. So this is called the head to tail method. Now what ends up happening here is that b is strictly to the left, a is strictly to the right. So if a vector is strictly in one direction, that means it doesn't really have a component in each direction. B serves as its own component, A serves as its own component. So what happened here is that these two would just combine, and if I draw the resulting, I'm going to go from start to finish. I would draw an arrow that goes straight from the butt of B to the head of A, and this would be my resulting vector. And notice here that when A and B are strictly in those individual directions, like to the left and down, is what they create is a little right triangle. Okay, so as we start to get mathematical with this, I can indicate here, notice there's another right triangle, that some right triangle math is going to come into play here to figure out what those vectors would add up to. Okay, all right, now for C I have two vectors, A and B, but now notice both vectors have components. A is pointing to the left and is pointing up. Okay, so I can label that, let's say, AX and AY. And then I also have the same thing for B. B is going down, that's a large vector, and it also is going to the left, BX. So if I wanted to add these two vectors together, again, I can show it using the head to tail method. Draw this as best as I can. So I'll draw B first. So B looks something like that. Okay, so that's B. And what I'll do to draw this is I'm just going to draw A off the head of B. Now A goes up and to the left, so I have to go back something like that. So there's A. And what ends up happening is they form a resultant from the start of B to the end of A that would look something like this. Now to kind of show you what's going on here with the components, again, B has a component that goes down and left, and A has components that goes left and up. So notice when I start to split this into directions, notice how I have two left arrows. So those two arrows would combine together. And then for the up and down, I have a large arrow downward and a small arrow upward. So those two kind of cancel each other out. So notice this goes back to example 1, where when I look at the components, essentially what I'm doing is splitting things up into directions, and then all I'm doing is using my rule of whether I add the components together or I would subtract them depending on whether their directions are in the same, or are the same, or if they're in opposite directions. So notice as we did that I was starting to form some right triangles, okay? So this means that as we get into solving problems with components, that we're going to have to use some right triangle math. So the first thing that you might remember from math class is some of the properties of right triangles, and some of the math properties we're going to deal with is things like Pythagorean Theorem. Pythagorean Theorem was looking at the relationship between the lengths of the sides of a right triangle. So Pythagorean Theorem related the three sides of a right triangle, what are called the two legs, A and B, and what's called the hypotenuse C, where C is that side that's going to be across from the 90-degree angle. Okay, and what Pythagorean Theorem states is that the sum of the squares of the two legs will equal the square of the hypotenuse. Now, this being said, using my vectors in individual directions, I can actually use Pythagorean Theorem to find the resulting vector. So take, for example, A, I have 11 kilometers north and 11 kilometers east. So this would be like a motion problem. Okay, so 11 kilometers north means that I have a component that goes north. I'll just label that 11. Then I'll draw the second one off of this, so that's 11 kilometers east, and they're going to form a resulting vector that goes up and to the right. So I'll label this R because that's my resulting. Notice when I draw these together, I get what formed out of them is a right triangle. So components in the x and components in the y will form a right triangle. And if I want to find r, think of these sides, the 11s, as the a and b, which are the legs, and think of r as c, the hypotenuse. So if I can use Pythagorean theorem and say, okay, if I square both the 11s and add them together, that then would give me or help me to find the resultant vector squared. So what I have to then do to solve for r is whatever I would get for the sum of those two squares, I would just then have to square root that value to give me the resultant vector. All right, now I'm going to use the decimal form. I know in math class you might learn about simplest radical form, but we're just going to use decimals because that makes sense in real life. So if you plug this into a calculator, yeah, you might get 11 radical 2, but you also might get the decimal of, let's say, 15.6, I'll round that, kilometers. So when we look at this, again, we're going to use the decimal answer just because in a real life sense, 11 radical 2 doesn't really make sense to me. Hey, I went to the mall, and it's about 11 radical 2 kilometers away. That really doesn't make sense, but if I say about 15.6 kilometers, that might make sense to me. Okay, so I can use Pythagorean theorem to find the value of this resulting vector. Now, the key thing here is that this resulting vector, Pythagorean theorem only gives me the magnitude or the amount of motion that I have. It doesn't indicate direction because 15.6 kilometers, this direction would be up and to the right. So we're going to have to devise another way to indicate the direction of that vector. But for right now, Pythagorean theorem is helpful to find the magnitude of that resulting vector. All right, so what I want you to do right now is pause the video, and I want you to try B and C. So here, instead of a picture, give you the words, but you might want to try and draw a picture similar to what I did. Draw a right triangle given the components, and see if you can find the magnitude using Pythagorean theorem. So go ahead, pause, give this a shot. All right, taking a look. So for B, you should get 11.2 kilometers, and for C, you should get 50 kilometers. Now, as I did B and C, notice, like, if we think of direction, and this is getting a little bit more into math and also with some of the things we're going to talk about. In A, I gave you an up and a right, so both of those are positive directions. And for B and C, I gave you a west, and I also in C gave you a west and a south. Now, I didn't show this, okay, but I wanted to talk through it first. But know that anytime we have direction, like that 5 kilometers west in B, that is technically supposed to be a negative. But the neat thing about Pythagorean theorem is that if I treat that 5 as a negative and use parentheses, it ends up balancing it out. So in this case, Pythagorean theorem is just looking at the magnitude so that by squaring that 5, it takes away that negative direction and makes it into a positive 25. Same thing here, this should technically be a negative 30 and a negative 40. So if I made both of these numbers negative, I need to make sure that I use parentheses, and again, it doesn't really matter here because the square is going to make those into a positive number. So again, Pythagorean theorem is helpful to find the overall magnitude or strength of that resulting vector dependent on those two components. Okay, so this was some of the basic properties and things about vectors. So we're going to get a little bit more involved. You'll notice that I'm not going through the trigonometry stuff yet. We're going to do that in class. So make sure if you have any questions, jot those things down. Otherwise, we'll see you in class. Peace out.